Okay, this should summarize or give you the notes about Chapter 8, Linear Regression. We've been doing this since Algebra 1 where we fit a line to some data, but now we really learn some of the statistics behind it, which I think also helps us understand the interpretations. So we were talking about a model. Modeling is a pretty big buzzword in mathematics. It's basically trying to find a pattern to data. And we find out that, lines are pretty simple and effective. And so we work a lot with trying to fit a line. And even when lines don't fit, we figure out a way to do that. More on that later. The notation is going to be a little different. Most of us are pretty familiar with y equals mx plus b. Well, now we have y hat. That's the predicted value. We say y hat is equal to, and now we put the vertical intercept or the y-intercept first, which makes a lot of sense because it's often the initial value. What's the cost of the program just to begin with, even without a monthly cost, something like that. So plus the slope, and now instead of m, we're using b sub 1. Times the explanatory variable or the input. And we also now are going to be talking about residuals, and residuals, a residual is the difference between the observed value and the predicted value we get from the model. So the model gives us y hat, but there was probably, we know that I'll show you this down here. We know that lines don't always fit the original data points, so the residual is the difference between those original data points and what the model is going to predict. And the line of best fit we're working with here is called the least squares line. And what does that do? It's the sum of the squared residuals minimized. So if this is our model, from here we get y hat. All of these were the original points that we fit the line through. And so if we take the difference, the actual y value minus what the model predicts, and square it, the actual y value minus what the model predicts and square it, the actual y value minus what the model predicts and square it, we add all those up and we want to get what would be the minimum of that. And twice I'm going to reference this math box on page 175. This is my one favorite lecture to do. I'm still not great at it. But essentially it goes through not only why the correlation coefficient R is relevant to the slope, but also how we minimize these squared residuals. It's kind of interesting if you find yourself and you want to go through it. In the end, notice it's a parabola that opens up, and so we want to minimize that parabola, and how we do that is all explained here. Anyway, kind of a fun math box. If I was with you, I'd be explaining it, doing my best to bore you with a lecture. All right, this is a lot. So this whole idea of correlation, we've been talking about the correlation coefficient R. So we take our data and we turn it into z-scores. And then we plot those z-scores, the z and the y versus the z and the x. And again, we're all pretty familiar with y equals mx. Since the best fit line would go through the mean, if we're talking about z-scores, then it would go through 0, 0. Remember, a z-score is how far you are, essentially the number of standard deviations you are away from the mean. So the center 0, 0 would be the mean point. So if we go through 0, 0, remember this plus b is 0. But we're not just talking about y equals mx, we're talking about z-scores in the y direction and z-scores in the x direction. And the line of best fit has a slope that is equal to r. That's like a whoa. Again, that's explained on the math box. Why the sum of the squared residuals has a slope equal to that r. R was, if you remember, the sum of the z's in the x times the z's and the y's, I think divided by n minus 1. Forget how we actually calculated that. Something like that. It's all mathematical. So I'm going to rearrange this a little. I'm going to substitute r for zx, and then I'm going to isolate r. So what else does that mean about r? It means that r is equal to the predicted z-score for y over the known z-score for x. So what does this mean then? It means that it's a ratio of the change in a standard deviation of y for every change in a standard deviation of x. So in other words, it's the number of standard deviations you move in the y direction in the response variable for each one standard deviation you move in the x variable or the explanatory variable. I'm going to come back to this. So if I'm plotting weight versus height, suppose I go up 1 standard deviation in height. If I go up 1 standard deviation in height, am I going to go up 1 standard deviation in weight? No, because it's not a one-to-one relationship. I can't entirely predict weight from height. So if I go up 1 standard deviation in height, I'm going to go less standard deviations away from the mean in weight. And it's the reason why r is between -1 and 1. Remember, we might be going down, we might be going up, and only if they were perfectly matched would r be 1. Like, again, if you're using a formula such as converting Fahrenheit to temperature, then you get an r to 1, or kilograms to pounds. Anyway, that's why r has to be between -1 and 1. There's not a perfect prediction between height and weight. And it's also why we call it a regression, because we're regressing towards the mean. If I go up 1 standard deviation in height, I'm going to be less standard deviations away in weight, so I'm actually going to be closer to the mean. I know it's a lot to think about, but I'll say it. You don't have to repeat it back to me. All right. So let's get back to this new notation. We have y hat equals the initial value plus the slope times the explanatory value. So b1 is the slope. We used to call it m. And it's equal to r times the standard deviation in y over the standard deviation in x. And if we want to find b, so we know what the standard deviation in y is, we can find it, standard deviation in y, and we can find the standard deviation in x. And we know what r is. And if we want to find b naught, we substitute a known point. Again, we talked about why that line would go through the mean point. So that's how you'd find b naught. That's how you'd calculate the slope. Remember, r is the number of standard deviations I go in the y direction for every 1 standard deviation in the x direction. We're going to talk a bit more about this later. Let's go back to residuals. Again, the residual is the data value minus the model value. We use a little e, y minus y hat. Therefore, a negative residual means the model must have been higher than the data. Therefore, the model overpredicts if you have a negative residual. If it's positive, it means the model must have been lower than the data point. Therefore, it underpredicts. Like if we're trying to predict price and we have a negative residual, our model is probably predicting a higher price than we can actually expect. And we can find a standard deviation of the residuals. We don't do a lot of this. It's introduced. I don't use it much. We don't talk about it much. But it gives you a pretty good indication, again, of how variable your data is from the model. So when you are doing a linear regression, and we're going to do this in my example that I do a linear regression on the other video, you should check the residual plot. I'll show you how to do this to determine the appropriateness of the model. There should be no observed pattern in the residual plot. So if I'm looking at a plot of the residuals, in this case I see fanning. So what's happening? My later data values are farther away from the model than my earlier data values, so something fishy is going on. If I see some kind of curved pattern, it's likely that I don't have the right model. If I don't see a pattern, if it's kind of boring, things are sort of evenly dispersed, that's okay, but you should really check the size of the residuals, because if you're if your predicted values are very far from your data values, then your model probably isn't very useful. So I do that in the other video. I talk more about that and show you how to do that. Now here's the next cool thing. We use a capital R squared, which is really just the correlation coefficient, the lower R squared. Don't ask me why, who makes up these rules. But basically, if you take little r and square it, all of a sudden, for some reason, it becomes a big R squared. R squared is powerful in that it gives the fraction of a data's variation accounted for by the model. And therefore, 1 minus R squared is the fraction of the variation left. That's also explained in the math box. So here's an example. Suppose I'm looking at house prices. I'm looking at price versus size. And I get an R squared value of 0.595. What does that mean? That means that 59.5%, right, because this is a fraction, you can express it as a percent, 59.5% of the variation in house price can be explained by variation in size. Now think about that. That makes quite a bit of sense. Like, yeah, the bigger the house, the more expensive it is. But there's going to be other things involved. Might be how insulated it is. It's going to be the how fancy the what do you call them? Like the light fixtures and that kind of stuff is. And so there's a lot of other stuff that's going to go into how expensive your house is. But size can explain 59.5% of that variation. Now here's the other thing we want to think about. The book goes through an example of, I think, Burger King products, and we fit a regression model to explain fat from protein. And the question is, can I then just reverse that model and predict protein from fat? Well, let's look at the equation first of all. It's y hat, in this case it would be fat is being predicted from protein. So I can't now just, predict x using a known y, because in the equation this has to do with a predicted y, not an actual data y. So that's kind of conceptual, but let's look at it mathematically. So here's my equation mathematically. I'm going to predict fat, and that's 6.8, this is grams. Grams of fat is equal to 6.8 plus 0.97 times grams of protein. So here's my model. I'm losing the hat. I'm just using fat and protein. Now you do this, I think you've done this in math where we find the inverse. So how do I find the inverse? I'm going to subtract 6.8 from both sides, and then I'm going to divide both sides by 0.97, and therefore P is 1 over 0.97 F minus 6.8 over 0.97. Incidentally, 1 over 0.97 is 1.03. So this new slope is just the reciprocal of the original slope. However, let's go back and think about in our model, statistically, where does this slope come from? Remember, it's our R, our correlation coefficient, times the standard deviation in Y over the standard deviation in X. So in this case, the correlation between fat and protein is 0.83. And the standard deviation in fat was 16.4. The standard deviation in protein was 14. So if I do all that, I get 0.97. That was my slope. Right? Now, what if I invert that and I say, look, okay, now I want to try to predict protein from fat. So now I do R times the standard deviation in protein divided by the standard deviation in fat, and I get 0.709. They are not reciprocals. We saw up here that the reciprocal of 0.97 is 1.03. So you can't just, mathematically we sometimes do this, but it's not really okay. There's an entirely different model with a different slope if we're trying to predict protein from fat. The curious thing is the R doesn't change. The correlation between between those two variables is the same, but it's this tricky business about the standard deviations. So finally, and again, we're going to talk more about this in Chapter 9, which is regression wisdom. But when you are fitting a line to data, you've got to ask yourself some questions, assumptions and conditions. Well, I'm looking to decide, is it straight enough? Can I even put a line to this data? And then the your book is, kind of cheeky, and they use this, does the plot thicken? And what are we really talking about there? We're looking at a residual plot. And then finally, you got to ask yourself about outliers. Are there any outliers? And what happens to the regression line and the R value with those outliers and without those outliers? So anytime you're doing a linear regression, you really have to check those things. So other than that, I think it's relatively self-explanatory. There's quite a bit of interpretation. I can go actually back and think about this. So this is our initial value. This is, if I'm looking at grams of fat, this is saying that even if I had 0 grams of protein, right, I'd still have 6.8 grams of fat. That's the initial value, the y-intercept. And then what's the 0.97 mean? For every 1 gram of increase in protein, I'm going to get a 0.97 increase gram of fat. Remember, your slope is your y over your x. So I'm going to go up 0.97 grams in fat for every 1 gram of protein. But that is all comes from this idea of the correlation between these two variables and their standard deviations. It boils down to that slope. There's some good examples in the book. Follow those. Do the questions. Check them. And then there's a couple you have to submit.